Let me get the chat open.
Oh, yeah, Dr. Barnhart.
Yeah, what's up?
Remember when you showed us your solar array on, was it Monday?
Yeah,
Your solar. How
yeah,
much do you burn in one day? How much do you use? How much power do you use? Because you showed us how much you make in one day. How much do you use?
yeah. Good question. So before I had the array installed, I used about 16 kilowatt hours per day, which is pretty low for the size of my family, a family of four, um, and the size of my house. And that's because I have pretty efficient appliances and lighting and things like that. And I don't heat or cool my house with electricity. And so that's what they sized it for, 16 kilowatt hours a day, which ended up being a 5 kilowatt array of panels. And in the summer, they generate 25 to 30 kilowatt hours. And then in December, they generate maybe 2 kilowatt hours during a day just because of the seasonality of sunlight here, way up here in Bellingham. But then once we got the solar panels, I really wanted to see how much energy I could make and not use. And so I became more fastidious about using less and less energy. And I got it down to about 10 kilowatt hours per day. But then this summer, I got a plug-in hybrid electric car. And so now I'm blowing it out of the water because I put like 13 kilowatt hours into that every day. So now I need more solar panels because one of my main consumers of energy, all of us really, is transportation, buildings, and then industry, which we'll talk about today, stuff. And so I was taking care of 1/3 of my energy, buildings, but then I just added another third onto my solar panels with transportation. But it's cool that car gets about 30 miles before it switches to gas mode. And so far, since owning it since June, and mainly it's truly like my wife's car. She's the one that uses it. We've only put like 1 tank of gas in it. It's gone like 800 miles on electricity and like 400 miles on gas. So it's working out great. It's a nice like bridge before we go fully electric.
That's pretty cool.
Yeah.
Yeah. Right. Just curious.
Yeah. Later on in the quarter, when we talk about solar and wind energy, I can show you some more details about my array and the seasonality of it. You wouldn't think Bellingham would be a good place for solar energy because we're so far north and we're so rainy, but our summers are dry and summer days are really long. So you actually can kind of make up for it in the summertime. And that's, of course, with a grid connected solar array so that I can still benefit from electricity from the power grid during the winter. If I was off grid, I would need some form of energy storage. What do you use to heat and cool your house with? Wood.
Okay.
And then, I mean, we live on the water, so I cool my house with the Puget Sound and I open a window. I don't live right on the water. I'm talking about Bellingham in general. So, yeah, if you need an air conditioner in Bellingham, you might be doing things a little wrong. Heat pumps are another story because they're much more efficient. And I understand if you're in the upper story room, then they do get hotter and it's more difficult to cool. Yeah, I remember when I was in college in Seattle, I lived in like the closet of an attic room in Seattle, and it was miserable. It gets so hot in the summer. But then I was in grad school and postdoc down in California, and I just sleep outside if it gets too hot. Okay. It is 2:01. How many people do we have? We're up to 70. Yeah, let's get going. I can't hear him anywhere. Anyone else? I can. Sound is fine here. Okay. Yeah, if you can't hear me, keep fiddling around. Make sure with modern like computer monitors and speakers and Bluetooth headsets and stuff, you may be sending your sound somewhere you don't want it to go. It could be going to your monitor when you wanted it to go to your headset or your speakers or something like that. So On Windows or Mac, go into your sound preferences and see what your playback device is. Okay, so today we're going to talk about stuff. And this is the last lecture on personal energy use. And then Friday, we're going to have a homework study session where we work together on the homework. All right, so the things you own end up owning you. This feels really true as of late. I had an issue with my house. The upstairs bathroom flooded, and now I have some water damage back here in the corner of my room. And it's fine. It'll be taken care of. But it's just like the more stuff you own, the more it pisses you off. Okay, so let's look into how much energy it takes to own stuff. So far we've considered energy use at the point of use, making hot water for coffee, heating and cooling, lighting, gadgets. That's what we covered Monday. But there's this whole ecosystem of energy use that's beyond the direct use of energy, where you can actually, flip a switch and see something happen, turning on a light, boiling water, etc. There's all this energy being used far, far away in factories that are manufacturing goods for you. We talked about it a little bit in terms of food production, right? And so to study how much energy is associated with all our stuff, we have to use a science called life cycle assessment. We also track carbon and toxins and other forms of harm using this study of life cycle assessment. It was developed in the late 70s, right after the oil embargoes, which is before your time, before my time. But apparently the world ran out of energy because they got in a war, kind of a common story throughout the history of man and women. But the oil shortages. And so America started really tracking their energy use, and is focused purely on energy at first, but then they said, well, we should track all sorts of things. And so then this field of life cycle analysis or assessment was developed. And that's actually what I research. That's what I do. Specifically focused on energy and carbon. Okay, so let's look at the life cycle of a t-shirt. Raw material, that's where it begins. So it starts out with some fertilizer, energy, and water. Or more likely, not fertilizer. Fertilizer actually comes from natural gas, but that's beside the point. Most of your t-shirts are probably made out of polyester, or a blend of cotton and polyester. And so polyester is actually just made out of oil. There's one of the biggest companies in India, Reliance, started out as a small t-shirt company, and then the owner wanted more control, so he started buying the factories that made the t-shirt. Then he wanted more control, increased profits, and then bought the oil refineries that provided the oil for the t-shirt factory. And now he actually owns oil drilling rigs and oil drilling platforms and production platforms to deliver the oil to his oil refiners and deliver that to the t-shirt factories, and then finally make the t-shirts. Also does a lot of farming and fertilizer and stuff. It's a massive, massive company in India. All right, so start off with oil. That's the raw materials, or fertilizer to make cotton, energy and water. Then you need to process those raw materials. So this requires even more energy. So you can't just throw cotton on your body and expect something to happen. You have to weave it and loom it. More energy. If you want it to be a certain color like blue, then you gotta dye it. And then you manufacture it. You cut that fabric into a pattern, make a t-shirt, and then you got to sell it. You got to make it look cool or something. And so you got to package it in something and ship it somewhere to the store. And then once you have it, you're going to continue to use energy to clean it, detergents, bleach, water, etc. And then finally, when it gets all raggedy, you can either dispose it, throw it away. You can reuse it. You can turn it into a rag or some other use you would care for. And then ultimately, you can choose to recycle it. How to factor waste? Good question. You will be a genius in the field of life cycle assessment if you start to figure out the waste, because not many people keep books on waste, right? We keep track of how much energy we pump into our factories to make things, keep track of how much energy it takes to ship things around, but we don't really keep track of the energy required to dispose of things as of yet. Recycling in batteries is becoming a big topic of discussion. How do you recycle a shirt? Well, good question. I don't know. I imagine you could break down the polyester back into polymers and do it that way. I think most of our shirts go overseas, actually, but yeah, I'm not exactly sure. Okay. All right, so this field of life cycle assessment, it's been formalized over the years, and so we use some vocabulary with it all. And it starts out with these 5 different stages. The cradle, that's where it all begins. The gate, that's where everything enters the plant. That's the factory entrance gate. And then there's the factory exit gate. And then there's the grave. And then it's subdivided into raw materials, material processing, product manufacturing, use, and disposal. There's this really cool book. I forget the name of the authors, 2 German guys. It's called Cradle to Cradle. And so it's about designing things with secondary, tertiary, quaternary uses in mind. So, designing shoes that can be easily taken apart and turned into playground equipment, that sort of thing, or a park bench. The book itself is Cradle to Cradle. It's printed on this highly durable PVC plastic. So it's completely waterproof. Like you can read it in the bath, no problem. And the ink is this soy ink that denatures with boiling water. And so if you choose to, and they say you're welcome to, you can pour boiling water all over your book and it'll make all the pages erased, and then you can turn it into a journal. So the book itself is Cradle to Cradle. Kind of cute, I guess. All right. So the whole game of life cycle assessment is to track all these different inputs, the energy associated with it, the carbon associated with it, and toxins, et cetera. And that's how we start to determine how much energy goes into all the stuff that we use all around us. So let's do a little example. Welcome to respond in the chat or with your mic. And we're going to look at the production of a jar of peanut butter. So what are the raw materials to make peanut butter? Peanuts?
Peanuts.
Yes, good. So this is like some pretty hippie peanut butter if we're just only doing peanuts. Like you go to the co-op and you mash it up or whatever. Yeah, so if you want it to taste better, you put some peanut oil in it and put some salt in it. And that's pretty legit. That's all you really need. Some people start to put sugar in it to make it sweet. And then you can start traveling away from peanut butter if you put like emulsifiers and different, hydrogenated oils to make it really perfectly smooth. But that's more of like a problem back in the 80s and 90s. We don't really do that as much these days. Okay, so you got it. Peanuts, sugar, oil, salt. We should swap out sugar for salt. And then to make the jar itself, you need glass if it's fancy peanut butter, or polypropylene if it's not so fancy peanut butter. And then you have to brand it so it has paper and ink and cardboard and film and all that sort of thing to make these raw materials. And these aren't even raw materials per se. Like glass is made out of sand, and polypropylene is made out of oil. Paper is made out of trees. Ink, I guess, is made out of some kind of oil. Cardboard's made out of trees. Film's made out of oil. Kind of getting a theme here with this oil stuff, right? Okay, material processing. What do we do with this stuff? Or product manufacturing. We can kind of say these at the same time. Roasting peanuts, mixing, bottling mixture. Yeah. This is all good. Roasting, grinding, mixing. Jar production, lid production, printer, box printing, forming, shrink wrapping. And the thing about LCA or life cycle assessment, all of these processes, they require their own LCA, right? You don't just go out in nature and find a roaster and grinder. You have to make that. And the things that make that. And so LCA becomes this kind of infinite regress where you have to start thinking about all the inputs into everything and then amortizing those inputs over something like the roaster or grinder, because it doesn't make just one jar of peanut butter. It may make a million. So then you have to take the inputs to that grinder and divide it by a million to find the component of that grinder that actually went into making the jar of the peanut butter. And it starts getting crazy, right? Like, well, who made the grinder? They may have ate a ham sandwich at lunch. What went into that ham sandwich? And so it just goes all the way back to infinity, to whoever, invented the wheel 10,000 years ago. And so we truncate, right? So we don't really consider anything beyond about 95% mass or energy. We only look at the nearer inputs, unless they might be something massive, like, building a rocket to go to the moon. We would consider the machines that went into building that rocket or something like that. But this is a lot of what like Elon Musk focuses on. In some of the talks I've seen, he's always talking about, we don't actually build cars. We don't build EVs. We build the machines that build batteries, and we build the machines that fold metal. We're not a car company. We are a machine building company. And so he's always thinking about the machines that build the machines that build the machines in terms of sustainability and arguably profits. Okay. So product manufacturing. So then, these jars get packaged up, put in a carton, sent to a distribution center, and then sent to a retailer, so a grocery store, and then user storage and consumption. This shouldn't take any energy at all. Some people refrigerate their peanut butter. You don't need to. It's just fat and salt. Like, it's not going to go bad. It just makes it hard to spread on your toast. But, I have difficulty in my own house explaining that. But anyways, my life's pretty good if these are the problems that I have in my life. Peanut butter. Okay, so then once you're done, you recycle the jar, throw it away. So that's a quick example of what life cycle assessment is all about. I teach a class, Energy 466 in life cycle assessment. So if you go into the energy program or environmental sciences or something like that, you're welcome to dive as deep as you want to into this subject. Okay. So there's this term we use to describe the energy that went into everything we have, and it's called embodied energy. And it's an abstraction, right? It's a simulacrum or whatever of what energy is. So it's not that, if you're looking at these three objects here, 2.1 megajoules went into making this cup, 3.3 megajoules went into making this can, and 0.1 megajoules, remember mega is a million, went into making this pencil. So if I lit these things on fire, I'm not going to get 2.1 megajoules or 3.3 megajoules. It's not like a chemical energy contained in them available for me to use. It's the energy that the factory and the truck and everything burned to make that object. And so it's like a historical record of the energy in these objects. And so this is life cycle energy, cumulative energy demand, or embodied energy. Apparently embodied energy is the only phrase I can say, so that's what I use. So the embodied energy is the historical record of energy consumed to produce an object or a product or a service. Some people call it emergy, but that sounds disgusting to me. I don't know. I don't like that word. Okay, so embodied energy is the sum of all the energy required to produce any good or service, considered as if that energy was incorporated or embodied in the product itself. In the case of the can, is that virgin or recycled aluminum? That is virgin aluminum. So this is raw bauxite ore obtained from a bauxite mine, and that's aluminum oxide. And aluminum loves oxygen, so it takes a tremendous amount of energy to strip that oxygen off of it. So you shock it with a high voltage current, and then you throw coal at it, and the electricity and the heat makes the aluminum and oxygen molecules jiggle more, and then they become attracted to that carbon in the coal and glom onto the coal and become carbon dioxide, and you're left with pure aluminum. And then you pour that out into ingots and then roll it into things like cans. the aluminum you see in a can is already oxidized. That's how much aluminum loves oxygen so much. There's a thin layer of aluminum oxide on every can. And that's why aluminum's dull looking. It's not shiny. It's because you're looking at rust, not a metal. So yeah, a recycled can, and nearly like 99% of the aluminum used is actually recycled, because it's so energy intensive that it's very economically incentivized to recycle aluminum. Incidentally, we used to have an aluminum smelter. I don't know if it's closed down or not. I think they're closing it down, or it's already closed down here in Whatcom County. But aluminum, because it's so energy intensive, it's manufactured in places with really, really inexpensive electricity. And so Whatcom County was an ideal place because of all the hydropower here in the Pacific Northwest. Where else might be the cheapest? Not energy. I mean, you think like cheap energy, you think Saudi Arabia or something where there's a lot of oil. Where might be the cheapest electricity in the world? Any guesses? Niagara Falls. Yeah, that's a good guess. So hydropower is good. New Zealand, yeah, hydropower. The ocean, yeah, the ocean has a tremendous amount of energy. It's just not dense, so it takes a lot of effort to collect that energy. Denmark is an excellent guess. They have a tremendous amount of hydropower, but they really they make more money selling that power to Germany rather than Iceland. There it is. Yep, Iceland. So what's Iceland sitting on top of? What is Iceland? Yeah, giant volcano, geothermal energy. So they just have this energy that's free coming out of the ground, and so they produce that geothermal energy, and they run massive aluminum smelters that they sell, and then they power Reykjavik, and then they take the very hot water that's still in that that comes out of those geothermal plants. It's not hot enough to make steam to spin a turbine anymore, but they take that waste hot water and then heat all the buildings with it in Reykjavik. And then they take the wastewater from that and use it as their domestic hot water to take showers, baths, whatever. So yeah, if you take a shower in Iceland, it reeks like sulfur, but it's perfectly clean. It just has a sulfur smell. And then they take the extra wastewater that's still hot and they pump it through all the streets underneath the streets of Reykjavik. So ice and snow never forms on the streets. It's just because the streets are warm. And then they take that wastewater and they fill up this big tourist trap called the Blue Lagoon that's like heals you or something. Yeah. So it's pretty cool use of free energy in Iceland. What will happen if that volcano erupts? Game over, I guess. I mean, the last time it really went crazy was in the late 1700s, and it sent Europe into a nuclear winter for a couple of years, and the French Revolution happened. Which wasn't a bad thing, actually. Maybe for the people involved. Okay. So embodied energy of common materials. The y-axis is kilowatt hours per kilogram. And so this is, remember, kilowatt hours, it sounds like power, but it's power, kilowatt times time, hour. Power times time equals energy. So this is kilowatt hours per kilogram of materials. And here's a few different common materials that go into a lot of everything you see around you. So if I look around my house, I see wood floors, wood tables. And so that would be this. There's tons of plastic everywhere. The more you look around you, the more you realize most of modern world's just made out of plastic. If we were in a classroom right now up at Western, the tables, the chairs, almost everything you see around you would be made out of plastic. Usually things like wood and plastic are supported by steel or aluminum, and then glass and paper. Fossil fuel is interesting. So this is exactly what I study. I try to think about how much energy it takes to make energy, because this is truly like the metabolism of society. If you start running out of energy, your society goes into collapse. We've seen it many times: Cyprus, Easter Island, Roman Empire, British Empire, etc. And when we run out of oil, it'll be the American Empire too. So thinking about how much energy it takes to get energy is really important to continue to allow societies to grow and prosper. We'll talk about that towards the end of class, not this class, the end of the whole quarter. Okay, so pay attention to PET plastic. That's 30 kilowatt hours per kilogram, so per unit mass, and aluminum's 10 kilowatt hours greater at 40 per kilogram. So 40 for aluminum, 30 for plastic. What do you guys think? Embodied energy in a drink container. Should you drink out of aluminum or plastic? Again, this is one of those false dichotomies. There's all sorts of things that depend, but let's talk about it. So use your mic or enter into chat. Do you think there's more embodied energy in a plastic container or an aluminum container? Aluminum, recycled aluminum. So that's an interesting one. Recycled aluminum would take the least amount of energy. That's, yeah, plastic. Yeah. Aluminum can be used more time. So that would take, yeah. So I'm seeing a lot. Plastics can be reused too. BPA in plastics. Yeah, that's true. So this is one of those, yeah, false dichotomy things. Maybe you don't want to be drinking from plastic. Beer tastes horrible at plastic. You go to sports games and they only give you beer in plastic because I guess sports fans throw things. I don't know. Aluminum is better because it's mostly reused. Gross. Plastics are hard to recycle though. Yeah. So aluminum takes more energy per unit mass, but aluminum can actually weighs quite a bit less than a plastic container of equivalent size. So one can of aluminum takes about 0.6 kilowatt hours of energy, and plastic takes a little less energy, but it weighs more. The plastic bottle weighs more, so it takes about 0.7 kilowatt hours of embodied energy. So it's actually better on your taste buds and better for the environment to continue to use an aluminum can. And not to mention all the other downsides of plastic, you know, microplastics and nanoplastics in the ocean, BPA causing cancer, and other issues with it. And because aluminum's valuable, because of its energy intensity, its embodied energy, it's something that we hang on to after we're done consuming it, recycle. Yeah. What about glass? Yeah, that'd be interesting. So back here, glass was one of the lowest in terms of energy requirements, but they're certainly way heavier than plastic or a can. I don't know if it's 5 times as heavy, but it might be somewhere up there near plastic. Things certainly taste great out of glass. Porcelain, even better. Yeah, I don't know. Maybe the way to do it is down in Mexico, you like, when you drink a Coke or a beer, you bring it back to the store and you give them your glass bottle, and then you get 50 cents off your next Coke. And it's always coming in a glass bottle that's very cloudy and scraped up. So it's been reused again and again and again and again and again. It's probably the way to do it. Yeah. But what are the reduce, reuse, recycle, the 3 R's? The first one is reduce. It just means stop buying as much crap. And then reuse is the second one. That says reuse what you already own. And then finally recycle. It should be the third step, but usually it seems like, at least the woke people I encounter, it's like they're all about recycling. They're all about showing off how many LaCroix cans they have in their recycle bin. Okay. All right, so embodied energy and packaging. So this is paper and cardboard. The average American throws about 400 grams of packaging away each day. It may sound really surprising until you think about, packaging in paper. So even if you don't subscribe to a newspaper, I don't know who does. Maybe that's a problem with the world. But, junk mail, that sort of thing, paper that you use throughout your life. Glass is about 7 kilowatt hours per kilogram, and that goes into that packaging, and then plastics that we throw away. And then you can think about, maybe you don't have packaging and things coming to your house, but if you go to a restaurant or a cafe or something, here's a Starbucks, and it looks like California based on that street sign. Tremendous amount of packaging waste generated each day. The Starbucks that's on Western campus is I've heard one of the most frequented Starbucks in all of Washington State, just because it's the Starbucks on a campus with 15,000 some students, and so that's crazy amounts of waste being produced there. And then even if you don't use Amazon for everything, if you go to a store like Target or Walmart for your stuff, all that stuff did come in boxes, and the packaging is just hidden from you. Embodied energy in computers. So this is an interesting one. The average computer has 1,800 kilowatt hours of embodied energy. So this is a crazy amount. This is like I don't know. This is enough to power my house for like 5 months or something, 4 months. And so why are they so intensive? What's inside a computer that might require a lot of energy? Batteries and processors, yeah. So lithium is very energy intensive to make the battery, and silicon for the processor. So that's super energy intensive. Why is silicon so energy intensive? It's just made out of sand, What you need is the microchips and the chips and the processors. You need that silicon to be like 99.999% pure. You can't have any defects in the silicon, otherwise the transistors don't operate and you get math errors and your chip is slower and slower until it eventually breaks. There's different like classes of chips in a given generation. It has to do with their purity. They get tested, and the ones that aren't as pure are deemed slower and slower chips. So you have to. That's why they're in these negative pressure rooms, and everybody's wearing bunny suits to just keep that silicon as pure as possible. And incidentally, that's why solar panels drastically became reduced in price after 2013, because manufacturers they used to just be made with computer chip grade silicon, but you don't need that level of purity for a solar panel. And so manufacturers in Taiwan started manufacturing their own silicon rather than using chip grade silicon. And so the price of solar panels went way down. And now we have two different manufacturing streams for silicon, one for chips, one for solar panels. Also has things like copper and gold and things like that. In general, kind of the more expensive something is per unit mass, the more energy went into it. Copper and gold take a lot of energy because they come from ores that you need to refine and process. There's gold underneath my house. There's gold underneath your house right now too, in the dirt. It would just take so much energy to get those little flakes of gold out of the dirt that it's not worth it. And so it only becomes economically worth it when that gold is concentrated in seams or riverbeds or things like that. Yeah, so this isn't very sciencey of me to say, but the fancier something is, probably the more energy went into it. Okay. So if you take this 1,800 kilowatt hours and divide it by 2 years, 365 plus 365 days, that means buying a new laptop every 2 years averages out to 2.5 kilowatt hours of personal energy use every day. It's embodied, right? It's not like you're paying that 2.5 kilowatt hours every day. It was paid by a factory long ago. But having a laptop means that sometime in the past, 1,800 kilowatt hours of energy was consumed to provide that laptop for you. And so it's a good idea to let things last a little longer. You don't need to have the newest, shiniest thing. Things can run out. This is a study I did a couple years back on the embodied energy in batteries. The y-axis here is megajoules of primary energy, so that's like oil, natural gas, per megajoule of battery capacity. And basically these electrochemical technologies like lithium ion or lead acid are slightly more energy intensive than geologic storage, like pumped hydro storage where you push water uphill, or compressed air energy storage where you fill a cave with high pressure air. And that's because this is made out of more precious stuff, chemicals that come from all over the world, whereas these are just literally holes in the ground. The benefit of these is you can put them in a laptop. You can't put something like this in your laptop. You couldn't put something like this in Manhattan. You can put something like this in Manhattan. And this looks at how much energy gets stored over the energy invested in a lifetime. Generally, for electrochemical technologies, lithium-ion batteries are the best, just because they last a long time. Yeah, I did look at flow batteries. That's vanadium redox flow batteries. And interestingly, they have great, they're very energy intensive to get the vanadium, which is actually a byproduct of coal burning largely. But then they still have a low energy return on energy invested because they have poor efficiency. They're only about 70% efficient because they have these parasitic losses running the pumps, moving the fluids around the battery. The benefit of something like a flow battery is they last forever. They last way longer than the lithium ion battery. They'll last longer than you will. So if we can figure out that efficiency problem, then I think, yeah, flow batteries are very exciting. They also, you can decouple power and energy storage. You can scale them however you want to. So yeah, they're pretty interesting. Are rechargeable batteries better? Yeah, I'm only talking about rechargeable batteries here. Yeah, non-rechargeable batteries usually just kind of have more specific uses now. You should probably be using rechargeable batteries in your personal devices if you still have battery powered devices, because you can get rechargeable lithium ion batteries in AA size or whatever now. The only real reason for so-called primary batteries that you don't recharge are instances where you don't have the luxury to charge something, or you need very high energy density, meaning you want the thing to be as small and light as possible. So it's like a battery and a pacemaker. You can't recharge that, and you want it to be as small and light as possible. Watches could be a good guess, but that should all be rechargeable now too. Hearing aids probably want to be as small as possible. And then all sorts of military applications and space-based applications, right? Sending something to space is incredibly expensive, so you want it to be as energy dense as possible. If you're in the tip of the spear in the Helmand province in Afghanistan, you don't want to be lugging around a battery that's twice as heavy just because you can recharge it. All right. Embodied energy and paper media. So I think the only thing we really think about is probably junk mail these days, but still the average individual embodied energy of paper is about 10 kilowatt hours per kilogram. All your reading materials add up to about 2 kilowatt hours per day. Really depends on the person. Yes, I agree. And I don't know if we're talking about paper or batteries or what, but yes, all of this depends on the person. This is just averaged out over the American population, these values here. Embodied energy and big stuff. So we all use houses, apartments, buildings, cars, roads, whatever. New car requires so much energy because it's aluminum and plastic and sophisticated electronics and steel. And so yes, 76,000 kilowatt hours. If your car lasts for 15 years, that's about 14 kilowatt hours per day. The average American only keeps their car for about 4 years, which is really sad. You should keep your stuff longer, take care of it, right? Reduce is the first R. Sorry to be preachy, but I'm coming at this from an energy perspective. Small house, 85,000 kilowatt hours. So look at that. Like a car is nearly a house, and that's because a house is made out of lower embodied energy stuff, wood and wood and concrete and other plastics, that sort of stuff. So if the house lasts for 100 years, that's 2.3 kilowatt hours per day. So again, you don't always need the newest thing, but if you do get something new, try to make it last. And then concrete roads, 7,600 kilowatt hours per meter. This is insane. So it's every meter is 7,600 kilowatt hours for something like a freeway. So that's 2 kilowatt hours per day per person just to build these massive roads. Yeah, does a car require 7,600 kilowatt hours to make? Yeah, that's just to make it. And then after that, you still have to put either electricity or gasoline in it to have any use out of it. Okay, energy required for transporting stuff. Road freight, 7 kilowatt hours per day per person. Shipping in the ocean, 4 kilowatt hours per day per person. And so it's much more efficient to ship things via the ocean. Most things are shipped via the ocean. And this chart here is kind of funky. The y-axis is kilowatt hours, so that's energy, power times time, per ton kilometer. Now, what the hell is a ton kilometer? A ton kilometer is, let me get my pencil here. It's 1 ton of stuff moving 1 kilometer. So that's the energy required to move a ton of stuff 1 kilometer. A ton is 1,000 kilograms. So an equivalent unit would be 1 kilogram of stuff being moved 1,000 kilometers. So it's a way to measure. It's a lot of shipping is measured this way in terms of costs, the cost per ton kilometer, or energy per ton kilometer. Similarly with people, right? Airlines are always talking about passenger kilometers or passenger miles. How much does it cost to send one person, 1 mile? And so if flying 200 people to Hawaii, what is the total cost divided by the number of people and the number of miles, and that you get passenger miles. Okay, so shipping, it's not the fastest, but it's by far the most efficient way to move things around. And we can even make this more efficient by attaching things like sails to the ship or painting the holes with, hydrophobic paints so that it slips through the water. Rail is really, really good too, and it's faster than shipping. Rail's super efficient because there's much less friction between a steel rail wheel and a steel track compared to a rubber tire on an asphalt or concrete road. And they get up to speed and just maintain that speed, whereas road traffic is stop and go, stop and go, stop and go. Some road trucks are getting more sophisticated. They're starting to act more like trains where they follow each other as closely as possible using automated controls and sensors. But it's kind of a half-ass way of approaching the efficiencies of railway. Okay. Water for drinking, water for sewage, 0.4 kilowatt hours a day. No, that's not separate from shower water unless you live in Iceland. All right. Let's get out of annotate mode. Okay, energy for defense. Annotate, clear all this. So, long time ago, President Eisenhower said the world in arms is not spending money alone. It is spending the sweat of its laborers, the genius of its scientists, and the hopes of its children. Okay, so what does he mean by this? It means that we're using a lot of resources beyond just money. We're using energy and intelligence to create create the machinations of war. I'm not anti-military. I'm not anti-defense. I believe, maintaining the integrity and security of a nation state is very important for stable society. But I think we've gone a little crazy here in America because we have, enough nukes to destroy the planet hundreds of times over. And, I don't really know what that's for. So if we add up all the energy we spend on defense and divide it by 330 million people, the amount of people in the United States, then all of us each spend 4 kilowatt hours per day maintaining our borders and our military presence across the globe. I mean, we have hundreds of bases scattered across the globe. Just 1.4 kilowatt hours of that per day is for nuclear weapons. Nuclear weapons are so energy intensive because you have to separate uranium-235 from uranium-237. And those two masses are nearly identical. They're less than a percentage apart. And so to separate something in a particle, a mass separator, you have to spin that forever to actually separate the 235 from the 237. So it's incredibly energy intensive. All right, so this SAR bomb was the biggest nuclear weapon ever detonated above ground. I think the largest one detonated, period. You can actually see the crater up on an island in northern modern day Russia. The location in which it was detonated was released. It's very impressive, horrifying. So this is 58 megatons of TNT, or 70 billion kilowatt hours released all at once. Cool. All right. Energy for universities, 0.24 kilowatt hours per day. So if you look at all the energy that goes into all the universities around America, divided by the number of people that use the university, it's 0.24 kilowatt hours per day. And this figure actually achieved just for Western itself. I added up all the energy for Western and divided by the number of students that attend Western and staff, and it's 0.24 kilowatt hours per day. Why are universities so energetically cheap? Or efficient? That might be a better word. Why don't universities take much energy? What do universities make? No one's driving. Yeah. So many people. Yeah. High quality students, lots of people. Yeah. That's a good guess.
Out of date electricity systems.
Yeah. Electricity systems. We definitely use that. But
Do things in bulk?
What?
Bulk production, say
Bulk
like in the cafeteria.
Yeah. So we make some food and things like that.
And it's just education.
Yeah. That's what we're actually selling, right? That's what we tricked you all into paying for, is education.
It's all also like really condensed, so it's kind of like a city where you don't have to transport yourself very far. Everyone's living in smaller quarters using less energy.
Yeah, excellent
those
point.
live on campus.
I mean, they're modeled after the ancient universities of yore, like Oxford or Cambridge or something, and these were in towns that were designed before the automobile, and so they're very dense, and you don't require automobiles for transportation. In general, Europeans use far less transportation energy than we do because of the density of their populations. It makes economic sense for trains and for more walking and biking than it does here in America, where things are very spread out because it's all built post-automobile. And so the automobile really was part of the philosophical design of anything west of Chicago, basically. Talk about that later. Yeah, so universities make ideas. Ideas are energetically free, or they're 100 watts per person. And so, yeah. Similarly, some of the least energetically intensive businesses, so if you look at how much energy per unit money, things like financing and banking are really low energy because you're manufacturing something fiat, something that's just an idea. And money's just an idea. It's a marker for power and change and energy. Yeah. So here's your personal energy use summary. Stuff dominates. So if you want to reduce your own energy footprint, first thing you need to do is think about how much you consume, all the stuff you have in your life, and what's important, what's not, what adds to your happiness or your well-being, what's deleterious. Second thing you could do is not drive as much. Your car is and this isn't embodied energy in your car. This is transportation energy, filling your car with gasoline. Don't drive as much as the second biggest energy consumer. And then keeping things warm, keeping your house comfortable is the third thing. This is kind of non-negotiable, right? You have to keep your house warm or you die, right? You have 3 seconds without air, 3 hours without heat, 3 days without water, and 30 days without food. And so you got to keep yourself comfortable. This is non-negotiable, but you can heat your house with a heat pump, for example, and cut this in half, if not by a quarter, if not by 3/4. Flights is another huge energy consumer. And so I've focused a lot on these first three, and arguably these ones too, except for defense. But when I look at my own carbon footprint, not this last year, thanks to coronavirus, but like I'm a horrible person because of all the flights I take. But so yeah, limiting flights is another thing you can do. And when I use adjectives like horrible, know that I'm being hyperbolic. I'm not actually that. I actually don't care that much. Okay, so here's your personal energy use summary. Big hitters are stuff and cars. Okay, I wanted to spend the last few minutes in class looking at orders of magnitude. So what's an order of magnitude? It's a way of separating numbers by a factor of 10. So 30 is an order of magnitude larger than 3. It's actually how our senses work, right? If you want something to taste twice as sweet, you have to put in like 10 times as much sugar. Your stereo, if you have a fancy stereo, it's the volume is measured in decibels. That's an order of magnitude scale. And it's measured that way because in our hearing, if something sounds twice as loud, it's actually 10 times as loud in terms of like pressure waves. And so order of magnitude is a real natural way of counting and thinking. And this is order of magnitudes of energy scale. So like 1 joule, remember that was lifting an apple onto a desk. That's about the amount of energy in a match. Go up 3 orders of magnitude, so 1,000 times that. That's the amount of sunlight hitting a square meter of Earth above the atmosphere. Go up 3 orders of magnitude beyond that. That's the average amount of food you need, 8.4 megajoules, to maintain your health. Why is it so difficult to lose fat? 1 gram of fat, you have to burn 38 kilojoules. So it's difficult to get rid of fat. Okay, 3 orders of magnitude beyond average human diet, that's a barrel of oil. So what does that mean, 3 orders of magnitude? That means if we could eat oil, if you got a barrel of oil, you could feed yourself for 1,000 days. That's the energy equivalence of that. 3 orders of magnitude beyond that, 1 barrel of oil. So 1,000 barrels of oil is the amount of energy required to power San Francisco for a single day. So the terajoule, this 10 to the 12, that's a city-sized energy unit. If we wanted to go to a country-sized energy unit, maybe US isn't the best example because we use a tremendous amount of energy. You use something called an exajoule, which is 10 to the 18. Exa stands for 10 to the 18, joule is energy. So this is the energy use for America in 2008, which used to be the peak energy use. Why 2008? Why did it peak in 2008?
The recession?
Yeah, recession happened, and then our energy use dipped down for about 5 years. Now we're way past that again. But yeah, energy and money are intimately tied in modern day societies. Note that this is 100 times more energy than in that huge bomb I showed the other day. Okay, so going up from there, global energy use is 470 exajoules back in 2008. Now we're up to like 520 or something. And you can look at how much oil is left in the ground, 8 zettajoules. Amount of coal is about 4 times more than that, or 3 times more than that. And if we could actually harness all the energy hitting the Earth from the sun over the course of a year, we would have 5.7 yotajoules, which is a crazy amount of energy. There's this sci-fi idea that advanced civilizations might have their entire sun encapsulated in solar panels. It's something called a Dyson sphere. And we actually see objects in distant space that are just glowing in the infrared, which is curious. And that's exactly what a Dyson sphere would look like. Okay, switching over to power mode. So power is energy over time, joules per second. I'll go through this more quickly. Turbine, that's about 5 megawatts. This would be, this is 3 orders of magnitude greater than the solar array on my house, which is 5 kilowatts. So this is enough to power 1,000 homes. If you want to power an entire city, then you need something like a nuclear power plant. This is where you get into a gigawatt. There's also the DeLorean time machine. Global solar energy power capacity, if we, that's today, we have 16 gigawatts. I think we're up to like 20 gigawatts now. If you plug the entire planet, all of society into one of those kilowatt meters that I measured the tea kettle with, it would draw 15 terawatts. This again was back in 2008 when it used to peak. Now we're actually at 18 terawatts, mainly due to India and China, tremendous economic growth over the last decade. So we're at 18 terawatts of global power use. Tremendous amount of wind resources and solar resources that could power society 60,000 times over. And so that's where the future is, right? You should put your money on solar power for the future. Craziest thing we've built is the extreme light infrastructure laser. That's for trying to generate nuclear fusion reactions, trying to ram 2 hydrogens together to make helium and a lot of energy. Right now, that's energy equivalent. So it takes as much energy to do that as we get out of it. But as soon as we figure that out, this class won't exist anymore because we'll have free energy everywhere. Small star, 135 zettawatts. R star, 384 yodawatts. And the Death Star is 10 to the 32 watts. It's kind of off the scale here. I can show you that real quick. So energy comes in all different flavors: chemical, kinetic, radio waves, whatever. The energy associated with gravitational attraction is potential energy. And it depends on how heavy an object is, its mass in kilograms. The gravitational constant under which it's being accelerated, so that's meters per second squared, and how far away from it is from the center of the object that it's being attracted to, its height in a sense. So if you lift up a bowling ball or something, the potential energy, how bad it would hurt to hit your toe depends on how heavy it is, what planet you're on, gravity, and how high up it is. This would be in meters. And so what was the planet that got blown up in Star Wars? I should be more of like a sci-fi fan than I am. Anyways, Alderaan. Yeah, that sounds right. So if we modeled Alderaan after Earth, the amount of power to disrupt Earth instantaneously, like the Death Star did, would be mass of the Earth, which is 6 times 10 to the 24 kilograms, gravity of the Earth, which is 10 meters per second squared, and the radius of the Earth, which is 6 times 10 to the 6 meters. 6 times 6 is 36, times 10 to the 24 times 10 times 10 to the 6 is 3.6 times 10 to the 32 joules. And so that's how I figured out how powerful the Death Star is. All right, I'll hang out for the next 10 minutes, but that's it for today's lecture.
Thank you.
Bye.
Thanks, Charles.
Thank you.
Yeah.
Thank you.
I had a question for the homework.
Yeah, what's up?
So are we allowed to do it like on paper and then just submit a photo of that?
No,
Okay.
I'm sorry. Unless there's some accommodations, you need to talk to me offline. If you,
No, it's okay. I was just wondering. That might make it easy.
but if you only have a cell phone or something, then you can use paper.
Okay.
If you don't have access to, I'm not going to make you thumb type an assignment out.
All right.
But yeah, in general, we just need to start getting used to producing more professional documents before you graduate. Yeah.
Thanks.
Thank you, Professor Barnhart.
My pleasure. Any other questions?
I had quick ones for the 3 equations we need to know. I have 2 of them written down. What was the third one? I have power equals energy over time, and the change of energy is the equation. What was the third one?
The efficiency equation, which I haven't formally introduced yet, but I'll go over it really quickly. Clear all drawings. Efficiency equals energy out over energy in. So there's a natural gas boiler in my basement that I rarely use to heat my house, but when I do, natural gas goes in at 130,000 BTUs per hour, and it comes out at about 80,000 BTUs per hour. And so the efficiency of this is 8 over 13, which I don't know, is like 70% or something. So that means the amount of energy I get out of that boiler, I only get 70% of the energy I put in. The other 30% goes up the smokestack. So efficiency is a way of measuring the useful energy in an energy conversion. I like to think of it as what you get over what you pay.
Okay.
Now,
Is that something we're going to go deeper into?
Yeah, and the thermodynamics module, which will be the next week and a half or so.
Okay, cool.
The key thing is for this equation to work, you need to have the same units on top and bottom. So joules over joules, or BTUs over BTUs, or kilowatt hours over kilowatt hours. That's the only way this equation makes sense. If you start mixing units, then your efficiency calculation is going to be garbage. Yeah. Cool. 3 people left. Any other questions before I duck out? All right. Have a good couple days. See you Friday.
Thank you. You as well.